Thank you very much for that, Viv. I enjoyed that, and I love what you're doing with some of Einstein's field equations and the more exact solutions you're looking at. And something I hadn't seen before, although maybe I've just overlooked it, is what you're doing with the redshift, and I love that. I love the fact that you can get the exact term R1 plus Z squared term from the exponential term as well, that they're related. I hadn't realized that one. That was a lovely one. So
Yeah, it does make things significantly simpler.
yeah, it looks it. I think looking at the whole of relativity from, as you know, I did the calculation deriving relativity from the redshift as well, which also makes it much simpler, in my view. So I think this is a very lovely way to look at it, and looking at what's happening with the internals of particles as well, with the harmony of phases, with the difference between the slowing down of clocks and the speeding up of frequency, which you also illustrated with the way you're doing things. Still, I have a few questions.
Oh, sure.
Um, the first one is, I wonder, one of the supposed big differences between angular momentum, classical angular momentum, and spin is the two-valuedness of spin for spin half, or the quantized values of spin for quantum particles. The fact that fermions have plus or minus spin a half when it's measured. Do you have any thoughts on that? On how that comes?
Different. I mean, a photon can only, or particles can only spin this way or that way, and the two directions of spin are what are called up and down, or plus and minus. I think it would be, if it was called clockwise and anti-clockwise, maybe it'd make it a difference. But yes, and the reason why it's quantized, I said they can only spin one way or the other. They're the two directions of spin.
Okay, but when you measure them, are you saying that every time you measure them, they have to be perpendicular to the measurement apparatus?
Yes, well, they always are. That's why. I mean, the fact that they can measure what I showed earlier, the radius of the proton. You had a situation where the protons were accelerated a small direction in this small energy in this direction, and the electrons came in at hundreds, well, a few hundred. I don't know how, a few hundred MeV, 200 or 300 MeV or something like that, and that they were measured. That the diameter, the only way they could measure that diameter is if the protons themselves were exposing their front end, their end on the rotating photon structure to the photons. So they do orient that way, and.
Okay. I mean, to get that resolution, you need to go to hundreds of GeV, and that's what's done to get to those very short wavelengths. So it's GeV there to get to those very small wavelengths to measure that. I do have several other questions. Perhaps I should save them for a little bit and see if anybody else wants to ask some questions too.
Just a point of clarification, Viv, did I hear you correctly that you're saying the difference between spin up and spin down is the direction of circular polarization, left versus right?
The direction from which it is viewed, yes. I mean, a photon, yeah, it is the spin up or spin down, what they call spin up or spin down, is just the direction from which it's viewed. Now, you can only measure the spin of something that's approaching you. And the spin, I'm going to use this as an example. It can only go either like that or like that. It can't go like that. It can't go at an angle. And that's why you'll only ever see, I mean, you can't measure the spin of something moving away from you. You can only measure it moving towards you.
No, I understand, but the point is, my view on the difference in spin up and spin down is the difference in circular polarization direction. But I know that you feel that there's no physical difference between the two. It's just viewed from the opposite side. So I just want to clarify that you're still saying different from me. Is that correct?
Yeah. The difference of the way the photon rotates determines the charge of the particle. So a photon rotating this way
around its axis.
Around its axis. So its axis is going like this, and then it's rotating one way or it's rotating the other way. And that difference of that rotation determines the charge field on the outside. So the twist of the rotating photon determines the charge of the particle. That's why a particle, an electron, is differently charged from it has the negative field on the outside. A positron has the positive field on the outside, and all they're doing when they come together and release the energy, they are just able to release each other's angular momentum and zip off as linear photons.
No, I agree completely that the charge is the chirality of the rotation around the magnetic axis. I completely agree with that. But I'm saying that you saying that is also tied to the spin up, spin down in terms of which direction you're viewing it. Whereas I believe that that's a different difference. It's the axis of travel around the torus that's different. But we still disagree on that. Is that correct?
There are only 4 possible combinations, and the twist and the rotation. There are only 4 possible combinations, and the 4 possible combinations they give up using the electron terminology. The 4 possible combinations are a spin-up proton, or a spin-down proton, or a spin-up electron, or a spin-down electron. They're the only 4 combinations.
I agree 100%. I agree 100% with it.
Yeah, so do I. I mean, but the way I visualize it, I think what Ali's getting at is when you're talking about rotations for the double rotating photon model, there are 2 rotations. One is the rotation in the plane of the screen at the moment. Here's the photon going round and round that thing. Yeah. What's happening at the same time is it's also rotating around that direction. Yes. That's a perpendicular rotation. Now, one of those is responsible for charge, and the other one is internal spin in the way that I view it. And that gives you 4 different possibilities. But these are perpendicular rotations happening simultaneously.
Yeah, the rotation.
Both are required. Yeah. So that's the way I see it. Anyway, so.
Yeah. So that rotation that does that is responsible for gives the charge polarity. And it's interesting. I'm not sure, but I've heard a rumor that they've actually detected a negative field inside a proton, which is what I would expect to do. But the field is different from charge. Charge is actually the photons coming out at the circumference. The field is just a field. I don't know whether that's true, but because the information I gave was what was measured at Stanford Linear Accelerator, Hofstadter and his team in the 1960s, and that's 60 years ago. And I'm sure they've done a little bit more accurate since then, but I just haven't come across them.
Yeah, when we're looking at charge scattering at CERN and on protons, then yes, we were also seeing scattering that was consistent with, actually, it looked like a net 0 charge at very high energies in the asymmetric scattering of muons, positive muons compared to negative muons, which would imply there is some negative in the proton as well for it to cancel out at the high energies.
Well, the field will cancel out, but the charge comes from the photons shedding photons at the circumference. So charge and field are not the same thing, although they will have the same polarity.
Now, what I'm saying is when you get length scale sufficient to get inside the proton, so sub 10 to the minus 15 meters, that you see some evidence of both polarities of charge. So in lepton scattering.
Yeah, I'd like to know a little bit more about that. And obviously, there are a lot of people who have done an enormous amount of work at this at CERN and other particle accelerators, but I'm going to stick by this. That is the origins of charge.
Oh, no, I agree with you. I agree with you about the origin of charge. Obviously, I agree with you. Yes, we both reached the same conclusion independently. So, yes. Yeah, no, I agree with what the origin of charge is.
Mm-hmm.
I have one question.
Yes, Benny.
You said there's the mass of a photon. That's clear to me that it must be this way, but the question is, compared to the wavelength, on which length scale does the mass of the photon distribute for a real photon? I mean, you can have the theoretical photon is infinitely long. It's a wave that is infinitely long, but a real photon exists at a certain point, at least to some uncertainty. And the question is, what is the length of the mass distribution of the photon or linear photon?
Well, when it comes to the rotation of a linear photon, the center of mass is wavelength divided by 2 pi, which happens also to be the diameter of the rotating photon is also
So you mean
wave.
it's kind of as long as wide?
It's kind of cylindrical and it's distributed.
Right.
So,
The question is
yeah.
on what length scale is it distributed?
That's
So
a very
what's the
interesting question. But I'd have to say, when you're measuring mass, when you're measuring rest mass, you have to think about how you're going to measure it. And if you're going to measure a rest mass, you have to put it in a box. You have to
Yes. I mean, what you could
as
do
big as the
is
box.
you could have a laser beam and have a second laser beam that is perpendicular but not hitting it, but at a certain distance. And the question is, do the two laser beams deflect each other?
Correct, gravitationally. That's a good question.
Because you have one beam, and a second beam that goes across but doesn't hit it. It has an offset. And these two beams would bend each other, basically like deflect each other because of its mass.
The deflection you would get would be gravitational.
Exactly, but it's too little to measure in real time. But the question conceptually is, what is the length of the mass distribution? For a continuous laser beam, it would be an average, that's clear. But for a single photon, what's the length? I mean, in a circulating, in a electron, it's obvious that it distributes over the full 300.
One of the problems with photons is that they literally can and do change many of their properties. I mean, it's unfortunate that Martin passed away before he could get all of the information across. But they can't, I mean, we normally talk about plane polarized photons being emitted from radio and television transmitters and circularly polarized, but they can have all sorts. They can be elliptically polarized. Or when a photon's emitted from an atom, the time it takes the electron to go from one energy level to a lower energy level to emit the photon is much, much longer than the frequency of the photon. So there's a suggestion that they can have many wavelengths, and they come in many different varieties that, unfortunately, I never with contact with Martin long enough to find out what all of those are, but there are many different ones. And so trying to get a definitive one, all I'm suggesting is that when it comes to particles, they are just the single wavelength. And if you do the calculations, if you had two wavelengths going around, it just doesn't work. The calculations don't work. So the particle, and the other thing, Heisenberg's uncertainty principle is nothing more than the fact that he was trying to pretend that they were point particles, and you can't measure the position of a point particle exactly, but the whole photon is within that wavelength. And you can't, it's like trying to measure the accurate, if you've got a car and if you've got not a car, but you've got a marble somewhere and it's somewhere between New York and San Francisco, for example, and you're trying to measure the exact point of that, the marbles or the cars spread over a distance. You cannot, that's all Heisenberg's uncertainty principle is. And I know a lot of people thought to have said that because of Heisenberg's uncertainty principle, that causes things to happen. It doesn't. It's just that's the physical limit of things.
Mm-hmm. So how does that then relate to the double slit experiment? I mean, a double slit is so wide that a single photon kind of would distribute over an area that is actually as wide as a double slit.
Well, the double slit interference pattern only comes about because the two slits within the spread, the lateral spread of the photon's wavelength. That's the only reason it comes about. If the slits are too far apart, then you won't get any effect at all.
Exactly. Yeah. So that is kind of the. Yeah. Sorry.
May I say some things about this? Sure. About the double slit experiment as well, and about photons. There's several things to bear in mind. I'm not sure about the answer, and I'm not sure Martin would have been sure either. But we did discuss it quite extensively. So let me give you my best guess as to what happened. If you have an emission and absorption of a photon, that emission absorption takes place at the same point in space-time for the photon. So even in a laser beam, if you have sequential photons coming along that are one after the other, they're very close to one another, but they're not at the same point in space-time. They miss one another by the interval between the emission of one photon and the next photon. That's one thing. Second thing is that if you imagine an emission somewhere, there's some mass at some point. It emits, let's say it emits a very hefty photon, let's say a black hole-sized photon, and that emits that photon, and the photon moves, and then gets absorbed somewhere else or arrives somewhere else. So that mass moves as from one point to the other. How big is that distribution between those two? Well, the best guess would be that it's related to the length of the wave train of the photon. Now, you can play with photons. You can make them very, very short, in which case their wavelength is not very well defined, or most photons are really quite long wave trains, so thousands and thousands or millions or billions even of wavelengths. So I would think that the mass distribution of the photon was distributed, first of all, between its endpoints, which the rest mass of the photon is only really defined in the frame where in that frame where it's emitted and absorbed, because that's the rest frame of the photon. For that photon, the two things are at the same point in space-time. So the distribution between the start point and the end point is zero. So then you'd say that during that process, what you have is you have the photon distributed like a rod along between the end point and the two. So it's at one point, then it's extended, and then it's the other point. So and I think that's the best guess that I can give. And it does that with with something that depends on the wave train of that particular photon and how well defined it is within the. It's also an uncertainty principle between knowing the precise energy of the photon and its wave train length. There's an uncertainty relation between those as well. So yes, sorry. And then for the double slit experiment, the reason that happens is if you've got a double slit and my nose is emitting and the screen is absorbing photons, then for any photon that's emitted by my nose and absorbed by the screen, it goes through all possible paths that are the same length. They're all zero length, so it just goes through both of the two things at once. And it only goes through those two. And the reason you get an interference is because you've redefined the shape of space, which is not allowed, allowed, not allowed, allowed, not allowed. So that's why you get the interference pattern, because space is topologically non-simple anymore. It has something which distinguishes one path and the other path. That's not anything other than quantum than the path integral approach to quantum electrodynamics. So that would how you think about interference in terms of emission absorption QED. So anyway, yes, that was just a couple of comments.
It goes with what I was saying earlier, but Martin, there are many variations of photons, although the rest mass the so-called rest mass of photons apparently has been measured and got down to zero, like 10 to the minus 40 at maximum. So But there are still, it's unfortunate that Martin did pass away. He could have answered, given much more comments on this, but the photon, as far as particles is concerned, is that single wavelength that I described, but as far as optical photons and larger, there are many variations that are possible, and I don't know all of them. And
Martin, there is a paper in 2016 where Martin talked a little bit about this stuff. It's
What's it called? I mean,
Quicycle.
yeah, I think I looked in.
It's the one that includes the words heavy beat box.
Oh yeah, I've seen that. Yeah,
looks yes, it's up on the Quicycle website. So
yeah,
if you want to download it and have a look.
I think I did. Yeah,
I think that's the best thing we have on paper.
Okay.
Okay. Well, yeah, go on. Hello.
There's one unrelated thing. You mentioned that the Schwarzschild solution is not correct or not exact, at least. Have you looked at, say, modern or, say, textbook derivations of the Schwarzschild solution and actually found an error? Can you actually pinpoint? Can you pinpoint in the derivation here at that point there is an assumption that's incorrect or something?
Yes, that was done in an earlier slide. If you'd like me to get it up again, I can do that. Okay. Where are we? Yes, here's where the mistake was made. Einstein derived the 1 plus alpha over R terms, but he approximated them, and you can read it in his book paper. He approximated them to 1 minus alpha over R, and it was the approximations that were picked up and used in this solution. Yeah, you
I understand what I wanted to say, or what I read is I have a German version of an Einstein book, and since I'm German, I can read it. And he says in the 50s, it was written. It was a rewrite of one of his first things, and he says to the Schwarzschild solution that he verified basically the derivation himself and found it correct. And said, I cannot go into detail here, but he was sure about that the derivation of the Schwarzschild solution was correct. He said that explicitly in a later book. And I looked into the derivation and I couldn't see the error directly in the say modern time textbook derivation, not in the one from that time, when Schwarzschild did it himself, but the one that is usually applied in some of the standard textbooks. And I couldn't see where there was
there isn't a mistake, and Einstein is correct to say there isn't a mistake. The mistake is in the starting point. The mistake is where you write the equation down in the first place. Because what Viv is doing is he's looking at the physical reason for what's happening.
Yeah, I understand.
Yeah, so if you start
I just couldn't find the point where this assumption was put in. I thought it was coming out, but maybe I'm wrong. I could follow it, but I'm not sure where.
One of the things I'd like to point out is that I've seen people use very complex maths to show that the 1 minus alpha over R, or gravity stronger than inverse square, could lead to orbital recession as a regression. Precession, that Mercury's orbit would increase, and yet physically that can't happen. When you go through the mathematics, you just find out that they make it so impossibly complex, and they ask, oh, but show me where I've made a mistake. If you ever want, the way I've found out, the way I handle this is you have a look at their answer. I don't know if you've ever solved any of these maze problems where you find all these different ways through a maze. The quickest way to solve them is start. The ins can lead to many dead ends. But going back the reverse way, there's only one way. It's much easier to do them that way. And when it comes to wanting to have a look at the accuracy of maths, if you're uncertain about it, is start at the end, because that's the answer. It's like making your way back. If you make your way back and you find yourself coming across a discontinuity, it's easier to recognize it that way than to try and work your way through some very complex maths that's not going to get you anywhere. And that's what people use. They just go out with such complex maths that somebody could actually. Gravity stronger than inverse square means that, like the sun, let's say the effect of the sun on Mercury, stronger than inverse square means that it pulls Mercury's orbit in a little further than it would if it was inverse square, and it has to travel a lesser distance to travel around the sun, and traveling a lesser distance with a stronger force means it will arrive at its perihelion point a little bit earlier. And because it arrives a little bit earlier, its orbit will regress. I mean, that's the physics of it. And that's very easy to show with mathematics. But as I said, I've seen somebody go along and just say, this is why Mercury's orbit precesses when physics says it. Well, most people don't understand complex maths. And they just said, oh, well, it's like this guy who derived, Richard Klaus or someone who derived zero isn't zero. Well, that's what the mathematics tells us. Well, if he's made a mistake, it's very, very complex. How's going to pick them out? And everybody, because they're very impressed by Einstein's complexity. And I think a lot of that was just put in there to, and he didn't solve. I'm sure he was a good enough mathematician to be able to show why the Schwartzchild solution was wrong, but he didn't. And I think the reason he didn't was that if he showed what was going on, I think people would say, oh, is it that simple after all? And as it is now, he's regarded as one of the greatest. Look, he was, let's not kid ourselves, he was a great mathematical physicist. He was a long, long way ahead of his time. But
Absolutely.
people copied the complexity of his maths and come to all and just not been able to handle the maths correctly. And that's why I agree with his statement of visualize it and get some order of harmony in it. But he just threw in such complex maths that nobody thinks he could do it. Or thinks he's a genius, be able to do it, and they can't follow. And I think it's not that difficult.
Okay, thank you.
Viv, can I go back to something that I saw on one of your slides just to get some clarification on? You mentioned that linear photons don't experience relativistic corrections. Is that correct?
Linear photons are emitted by transmitters, radio, TV, that sort of thing. It's very difficult to get they probably can, but everything in the universe is rotations. And so all naturally emitted photons, be they gamma rays, X-rays, photons, are emitted as circularly polarized, but even some of them going through space, there are so many fields out there that they can turn around and be detected as plane polarized. That is, at the time of emission, because of the circular nature of every structure, all photons emitted are circularly polarized.
I know that's I get that, but you mentioned that linear photons are not subject to the relativistic corrections. And my question was really about A, neutrons, and B, antenna emitted photons.
Well, yeah, neutrons are rotating plane polarized photons. Yes, that's what they have, half positive charge and half negative charge. So, okay, it's not entirely. I've never checked to see whether neutrons actually emit photons or not. I've got no idea how. They probably do, although I think even when a neutron decays to a proton and an electron, you could correct me, John. I think when that occurs, I don't know of any photons being emitted, and most of the energy is carried away by the neutrino, the proton, and the electron. I don't know that any photons are emitted then.
Not necessarily, but neutrons, I think, have magnetic moments. So in principle, they can couple to photons through, but much more weakly than particles do. But linearly polarized light is just a linear superposition of right and left circularly polarized light. So the Lorentz transformations are just the same for linear as they are for circularly polarized light, or they should be anyway. So just linear combinations of one another. So,
but as Martin pointed out, there are many, many different variations of photons that I can only imagine. They don't all behave the same.
Well, they don't behave the same under rotations, but under Lorentz transformations, I think they all do, in terms of shrinking and expanding. Because right and left behave the same, so any linear combination of right and left will behave the same. For rotations, not, because if you, but for a general Lorentz transformation, not, but for a boost, they do the same thing. Well, at least that's what's shown in the beatbox paper, anyway, and for anything in between, and for any direction as well. But that brings me to another question. You say that the electrons can only move with the thing perpendicular to the direction of motion. If we think about the ring being perpendicular to the direction of motion, that means the electric and magnetic field, that means the pointing vector for inside the photon is in a ring going around my hand. Yes. Why can't the thing move sideways? I don't get why that you can't move that, because it's already confined, so it's a confined object. Why can't it move in a different direction?
The photon can be emitted at any angle. You know, emitted that way, and whatever angle you want. But once it's emitted, well, you saw the Maxwell's diagrams up earlier, that he just electric field this way, magnetic field this way, and the photon traveling in this direction. You've got to have a mechanism by which the magnetic and electric fields can move. If the photon is traveling that way, you know, like say travel that way, you've got to have a mechanism by which the electric and magnetic fields can move in this direction. Now, you can emit a photon in this direction, that's no problem, but there's no mechanism by which they can move that way. You can, instead of, you can have the whole photon emitted that way, you have the whole photon emitted that way. But if a photon is emitted that way, it can't do this. It can't move sideways, is what I'm saying. But you can emit them in any direction. But once it's emitted, that's the way it travels, and there's something in it.
Yeah, but if you've got the thing going round a ring like that, that's the photon going around a ring, and you move it this way, it is moving sideways. That is moving the photon sideways.
No, the point, let's say it will spiral like this. But the direction the point is the leading edge travels, still has the electric and magnetic fields perpendicular to it, is what I'm saying.
Yeah, that's right. But if it's traveling in a spiral, those perpendicular things are, so the spiral is R, and theta and z, the electromagnetic fields are the
Yeah, like I said, there are many unknowns about,
part of the time anyway.
there are many unknowns about photons, but
Yeah.
the thing is, if you allow it to a photon to be able to travel sideways, then you don't get the special relativity corrections, and then you have to come up with another physical and special all of these things. You can't just impose mathematics on top of something and say, "Well, this is describing how it works." You've got to have a physical reason for it. And at this stage, it's very difficult to come, even as the photon is spiraling, the magnetic fields and electric and magnetic fields are still perpendicular to that spiral.
So, Viv, then what would be the difference at ultra high velocities between the electron and the photon itself, if you know what I mean? Right? Because at ultra high velocity, that electron's spiral will be so stretched that it'll start to approximate a photon. In your view?
Well, it does.
Yes, I mean,
just like
I had a book once that I read. It was somebody by the name of Erdmann, and he called it the photonic structure, the partonic structure of photons, partons being particles, and what I'm suggesting is the wrong title. It should have been the photonic structure of partons, rather than because they observed that when you get to high enough energies, they can't tell the difference between a high energy photon and a proton. They have the same properties as would be expected.
Well, then I throw the question back to John.
He was talking about protons, but it's the same thing with electrons. If you've got a 1 MeV or half MeV, photon has about the same mass as an electron, and telling the difference between not easy. They have similar. That's what his book was saying, and he was ascribing it to the partonic structure of photons. And I've seen people trying to explain protons as combinations of particles, and then really it's the other way around. That particles are variations of photons.
Well, if I could pose the question to John, then, in terms of the electron, how would we factor in those other components of the spin at those very high velocities? If you know what I'm asking, right?
Yeah. Well, the spin remains half integral. Spin is absolutely conserved, and if you accelerate stuff, the spin remains the same. So any properties that depend on spin will still be there. The way they look the same is any kind of calorimetric experiment. So if you stick them into anything that forms a shower, so if you start trying to get the energy out to measure the energy, then electrons and photons at the same energy, sort of G look the same. Of course, electrons remain charged as well. So in a multi-wire proportional chamber, you see the electron bend and the photon doesn't. It goes straight through. So you can distinguish them, but they look very similar from the way that they interact. So the interaction looks very similar when they hit something. So, but spin is different for electrons and photons.
That's what I was saying before, that the author of that book would have been much better off if he wrote the photonic structure of partons instead of tried to fit photons into particles instead of trying to fit particles into photons. And I know many authors have tried to explain photons in terms of particles. Try the other way around. It's much better.
Well, you can do both.
Can I also ask another question back to your proton diagram with the harmonic resonances 1/3, 1/9, etc.? The thing that struck me was if you look at the different charges of the different harmonics of the 1/3 harmonics on the diagram, you have a reversal of the direction of the chirality. And my question to you is, within that harmonic, how could it, angular momentum wise, how can it switch chirality in the middle of one of its resonance rotations?
Well, it's just a conservation of just conservation principles. I mean, you within the proton, you have there's different structures, and the neutron is more complicated because you have a 1/27th as well. The conservation, all the principles of conservation still apply. And so basically these things pop into and out of existence as needed to conserve. So apart from the mass, like the magnetic moment is just an average of all of the magnetic moments that are generated by the various rotating photons. But they pop into or out of existence so quickly that any reasonable time period, probably reasonable, you're talking 10 to the minus 10 to 10 to the minus 15 seconds. If all you're ever going to do is measure the average. Because the primary photons rotating at 10 to the 23 rotations per second, and when you're doing that at a radius, well, that gives it a radius of 0.1 FM, and you got something traveling at the speed of light at the radius of 1 FM, there's one hell of a strong centripetal force. My suspicion is that that force is just so strong that it won't just emit linear photons like the electron, but that's where the 1/3 and 1/9 harmonics, they just get thrown out, because 1/3 and 1/9 or series of 1/3 frequency harmonics are a real pain in the backside for engineers, like electronic engineers, trying to get a pure sine wave coming out of their transmitter. They're just very, very difficult.
Well, let me ask it a different way. Is it possible that as those resonant rotations are going around, that when it goes to the negative one, the magnetic polarity flips upside down for that resonance? Before you answer that question, the reason I'm asking it is because my conceptualization of this is based on something John and I have been talking about recently, about these photon topologies are phase locked and at the speed of light, meaning you could almost think of them as stationary structures, because from the photon's point of view, it's at an emission and absorption simultaneously. So it's in the entire topology simultaneously in its own frame, is the way I'm thinking about it. So I'm seeing it as a continuous angular momentum, like it's a photon wavefront that's moving at the speed of light, so it can't reverse. So if it's going to keep going in the same direction, in my mind, it must flip for those. You hear what I'm asking?
Yeah, that's right. Yeah, that it just flips for the magnetic field flips. Although you're bearing in mind that they do the uncertainty principle sometimes means that you can't be sure exactly what is happening
at any instant, but if you're describing the overall structure, it has to still remain self-consistent. So, but even though I agree with your point.
Yes. That was such a long time ago that I did that, but I think that like you've got to have 2 positive and 1 negative for a proton at all stages, and that's what they observe. I mean, you can even collide protons together. You can even get negative muons out of them for that reason.
One of the things I really liked about what you said today, which I hadn't really thought of before, is when you were describing the charge profile of the proton, how those negative resonances were impacting on the shape of the curve as it descended, which I thought was very cool. I hadn't thought about that before.
That's what spreads them, and the only way that can be measured is if the rotating photon is always presenting the face-on of its rotation. And that's why it's measured, and that occurred at very low energies. I mean, 938 MeV or 937 point something MeV per c squared. I don't know, even if you gave it a 1 MeV acceleration, that's a very, very minor change to a proton. You know, it doesn't, and yet that's the that is measured. So protons or nucleons or any particles always orienting themselves to the direction of travel. And if you take, even if you could get something that rotated at 10 to the 9th RPM, 10 to the 23 hertz, or 10 to the 20 for an electron. These things are vibrating all over the place. They wouldn't even notice. They would just vibrate themselves anyway. And the fact that it has to vibrate a little bit more in one direction as it's rotating versus when it's stationary just wouldn't even be noticed. But if you've ever noticed, you get two large gyroscopes and you hold them and you try to twist one by itself, you can't. But when you put the two together and they're joined by a solid, and you both go very easily. Well, the difference is taken up by the nucleons themselves. They will transmit the angular momentum by changing their own. It's
Yeah, I think in the case of the proton, I have no problem with the I think you and John, even I would speculate, would agree on the fact that the molecule could be equatorially planar because those resonance structures are going to lock each other in. And so it makes sense that that individual elements would be harder to orient in a different plane. I think the electron is the only place where you guys may have disagreement on that point. But anyway,
well,
we are getting a bit late. If you guys want to, I don't know how much longer keep chatting.
Getting late. The sun's up and I've just risen at my end.
I've got one more question, Viv, and then which is that Mike saying bye bye? Yeah, I've got one more question, which is well, you're right. I mean, there's some very big forces, centripetal accelerations going on in the proton. In your view, or what are your thoughts on what's balancing that? What's making the photon go round and round in circles? In your worldview, of what's happening?
Well, I gave that indication before. Well, first of all, a closed magnetic loop is stronger than an open field. So if a photon has the opportunity to form a closed loop, it will. That's one of the reasons. I mean, the mass of photons, linear photons, is probably something like 1% compared to the mass of rotating photons. Photons prefer the
no, I understand all that, but if you've got for every force there must be a balanced force. So, but how do you see that balanced force? What's the counterforce for the centripetal acceleration? Not that it likes to do that or something, but how do you see that force? How do you visualize that force? What's it acting on or between or?
Okay, well, we go back to this situation. You have this as represents the circularly polarized photon comes in. I mean, it just gets compressed together. When they're compressed together, the magnetic fields just overlap. And once you've got an overlapping field, you have the continuous loop going through, and that continuous loop is why protons will rotate around the magnetic field.
You say the confining force is coming from field cancellation and like magnetic field cancellation, which is a reduction in energy, which is a strong potential.
Yeah, and the other thing to bear in mind, you've seen those diagrams I've given on the gravitational field attraction, where the quantum field has a. I go back to this one, and you'll see where this field is strong. When the mass gets really, really great, this field, the strongest attraction is outside the field. Now, if you've got this massive object, millions or billions of solar masses, under this model, neutrons, or protons and electrons, gravity can force protons and electrons into neutrons, and you get this huge mass. It will attract everything, including neutrinos, including photons. They all go into this, and ultimately you get to the stage where the massive neutrons start. You got a neutron star where neutrons can't collapse. It gets so large that the strength of gravity is outside it. So you've got this huge, massive neutron stars, but it's being pulled outward, which basically means that the pressure on, with everything being pulled out, the pressure on the inside of the neutron star diminishes. Once that occurs, the neutrons no longer have sufficient gravity to keep them in place, and eventually you get a crack in them and everything spews out. Well, all of the linear photons have gone in. They prefer to get wrapped up in the particles. And this is the reason why, I'm saying this is the origins of quasars. It's not a black hole that's going to keep pulling stuff in and emitting radiation. It's just these neutrons eventually breaking down into protons and electrons. And the pressure builds up. Eventually they form a crack. It'll always be at the top of the axis, near the axis of the neutron star. But what I'm trying to say is that all the linear photons and everything that went in there don't stay that way. They just get caught up in the mass of the nucleons, in the mass of the nucleons, because of the preferred rotating to linear structure. And that's how energy is that is how energy is recycled to go back. And when everything is fused, it goes into these, it gets released again as primarily hydrogen, which can be fused again. So the linear, my impression is that because of the closed loop nature of the magnetic fields in a particle, they are the more preferred state. The other thing that people may not be aware, I mean, in a linear photon, the magnetic field, because it's the same as the electric field, varies with r squared. But as soon as you have this closed loop, that's where the magnetic field variation, strength variation as r cubed comes in and makes it much stronger.
So you're saying that what's happening here is that you have something with the redshift metric, you have something which is like a hydrogen source. It's taking its energy from the gravitational energy that appeared when the thing was formed and recycling higher metals and helium back to hydrogen, which is emitted by such a thing and then can be fused again effectively.
Yeah. I mean, gravity, despite what people think, gravity reverses entropy. A tree grows up, when it dies, it falls down. Gravity reverses entropy. You get you get the old, or even sometimes you just get a mixture of oil and water, shake them up, and you've got even just surface tension will reverse the entropy as the two will separate out. Or you've got a dusty chamber and you just let it settle. The dust will fall down to the bottom. And so gravity reverses entropy. There's enough gravity in the universe to reverse any entropy. And the other way of looking at it is star formation from an enormous cloud of gas and dust. Well, obviously, cloud of dust and gas and molecules and dust is highly disordered. Just gravity pulls them into stars and planets. And gravity reverses entropy. So entropy is pretty good as long and it works if gravity doesn't take over. But gravity takes over and reverses it.
Okay, good. Okay, good.
All right. Well, I hope hope you can visualize. And I said, my use of visualization gave me quick understanding of an easy understanding of Einstein's special relativity corrections, or the special relativity corrections, plus through the extra one in, which makes an enormous difference in electron physics. It also what enabled me to work out how nucleons produce gravity. Just visualizing these things makes it enormously lot easier than just sort of sitting there and trying pages and pages of maths that have no physical meaning. Pages and pages of maths that have physical meaning, yes, very good. Pages and pages of maths, and I've seen it just going on and on and on forever with no physical meaning, and you come to conclusions that, yes, well, we won't go into that.
I just wanted to add two quick questions, but probably like some other time. It was related to what John has asked. First of all, really thanks for your talk, Arnie. I really enjoyed it, and I like the way you present it. Makes things much clearer, like, when you talk. The question was about the lovely question that you asked, like, why do photons rotate, basically, like, the angular momentum, like what's the existence of angular momentum. And so you did talk something about that linear is the more preferred state than the rotating in terms of stability. So I was wondering, in terms of like the preference matrix, I didn't really get that when you talked about it in your slides. And then the other one was about when you talk about the centrifugal force,
Yeah.
that the photon experiences while it's looping around, and it is the reason why you get charge out of it. I was wondering if you had thought about the absorption and emission mechanism for these photons, like how do they emit basically photons so that they can be observed as charge.
Okay, the splitting, photon splitting is well known from Compton scattering. Photon going back, photon uniting. I read a paper somewhere where they have found that photons can join, so that two longer wavelength or lower energy, lower frequency photons can join and form a higher frequency, but it always involves mass. So have I gone into a huge physical description of how the photons rejoin? No, I haven't. But it's known that both photon splitting is no problem, as Compton scattering has been known for a long time. Photons rejoining has been observed, but that always involved mass. In other words, I think photons were passing through a cloud of dust or something like that, and they came out the other end, or a cloud of something or other, and they came out the other end at higher frequencies. No, I haven't gone into it in great detail, but no, it'd be a good topic to study. Okay, thanks, Mark.
Thanks, Viva. That was great. I don't know if anyone else has any questions or comments, but if not, we can bring it to a close. It was a really great session. Thank you.
Thank you for listening, gentlemen.
Really good answer as well. You take care of yourself. Enjoy your breakfast.
Yeah. Bye.
Bye, everybody.
Bye. Bye.
Good night. Good morning.